Okay, can you see the slides on the screen? All right. So let's continue with etching. Okay, when we do etching, there are a few important parameters, and we have discussed some of this yesterday. Okay, so the first one, if you look at this table, is etch rate, or the film thickness that we etch or we remove per unit time. Okay, so it can be nanometer per minute, nanometer per second, micron per minute, micron per hour, for example. Okay, and this etch rate has significant effects on throughput. So if you have a very high etch rate, so that means your removal is very fast, you can remove the intended material in a very short time, and therefore that will make your process throughput higher. Okay, so you can etch more wafers in a short time. On the other hand, if your R is, hold on, ada mesej masuk pula. All right, okay. Yes, if you can etch with a very high etch rate, so that means you need less time to etch more materials. So therefore, your wafer per hour, remember, when you talk about throughput, then we are talking about wafer per hour, okay? Wafer per hour that you can process. So in all processes, so whether it's lithography, you're talking about wafer per hour, in etching, in implant, in diffusion. So we are using the very same word, throughput. So, and that means wafer per hour. Okay, throughput. How many wafers per hour can you process? Okay, and we want to have a high throughput for all processes, for every single process, okay? Okay, second one is etch uniformity, variation of etch rate throughout one wafer. So it can, just like what we discussed yesterday, it can be throughout one wafer, it can be wafer to wafer, it can be across different batches, it can also be across different equipment, for example, okay? But the whole idea is you want to have the same etch rate throughout the comparison, okay? So if you're talking about within a wafer, then you want to have etch rate to be consistent throughout that one wafer, across wafers, across batches, and so on and so forth. So the key here is still etch rate. So if you don't have uniform etch rate, you won't have good uniformity. Then the third one is selectivity, the ratio of the etch rate between two different materials, just like what we discussed yesterday about SiO2, which is etched by HF, right? Anisotropy is the next one. We discussed about the equation yesterday, right? You can recall the equation yesterday, this or this equals to vertical minus horizontal over vertical, then you can tell the anisotropy. If it's very one directional, then we call it a highly anisotropic etching process, okay? So A0 isotropic, perfectly isotropic, A1 perfectly anisotropic, right? Then the next one is undercut. Okay, undercut we have also discussed yesterday. Masuk dalam tu kan? All right. Another characteristic that you have to understand is CD. Okay, CD we have discussed in lithography, and we will also discuss in etching. Remember, let's recall when you talk about CD in lithography, what do we call the CD? Anyone? What is the word we call it? CD in lithography, we call it as what? Anyone?
Critical dimension in litho as in resist
Resist, yeah, resist dimension.
resist dimension. So maksudnya kalau in X dimension.
Yes, exactly. So, what do you call the CD in lithography after lithography? What's the term?
Don't know.
Anyone? DICD. Apa maksud DICD? What is DI? Anyone? DI? After etch is FI. Apa maksud FI? Develop, inspect. DICD is develop, inspect, CD. After develop lah. Okay. We develop, we inspect. FI is final CD. Okay. Final CD after etch. So critical dimension, final or FICD, the width of the final etch feature. The final etch feature, for example, in this case, you can see, say this is your resist on top, so that will be your printed feature size. If you're measuring the hole, Kalau measure line, then you're going to be measuring this or this for the ICD. But for FICD, you're measuring the etch feature. Apa yang you want to pattern actually? So in this case, you want to pattern the oxide by using the photoresist. So then in etching, you are measuring the pattern oxide rather than pattern resist, because resist will not be there after etch. So then the top one will be your DI, your bottom one will be your FI. Okay? Is it okay? Clear?
I itu apa?
I apa? Siapa nak jawab? Untuk litho punya, I dia berbeza maksud inspect, develop, inspect, CD untuk litho. Kalau FI dia tak pakai inspect lah, dia pakai, well, you can also say final inspection CD, that can be done as well. Yes, can use CD final. Tapi biasanya kita pakai final CD je. But then if you want to compare, then you can say final inspection CD. Okay. So remember the DICD, if you get it wrong, you can still rework. Okay, boleh lagi strip off the resist and redo CED. Tapi tengok kat sini, if you've got your FICD on the oxide, can you rework? Boleh rework lagi tak kalau dah ada FICD? FICD means you have etched the oxide, then you remove the resist on the oxide, and then you are left with pattern oxide on the silicon. Can you rework? Kalau you punya FICD out of spec, for example, can you rework the wafers? Anyone?
Tak boleh reward lah.
Tak boleh rework, lepas tu nak buat apa? Kalau you punya FICD out of spec, OOS out of spec, ataupun OOC out of control ni still okay. So out of spec, Kena buat apa kalau ni? Kalau apa all respect, you punya FICD?
Kena scrap lah.
Kena scrap. Good. Right, scrap. Gone. Habis. Tak boleh lah. Tak boleh selamat lah. Scrap. Gone. Kira you punya wafer tu kalau it has gone through say half of the process flow, then gone. Ataupun 3/4 of the process flow, gone. Almost completed, gone. Lagi teruk. That means you have spent so much on the fabrication processes only to get the final version of FICD at the final steps to be wrong. Okay. So habis. Kalau you scrap dekat final stage, kena pancung kepala. Okay, tak kena pancung lah, literally. Okay, literally. Don't take it too literally. Pancung means kena ngembas lah. Right, so yep, if you got your litho CD wrong, you can still rework, even though that's not intended. However, you still can rework. That means you still can save the wafers. FI habis. So etch bias is another parameter. What you see isn't always what you get, right? Etch bias is the etch feature size versus printed feature size. Whatever that you have etched, basically that means your FI like FICD minus DICD. FI minus DI or D equal to etch bias. Okay, there'll be some bias, but you want to minimize the bias. But there'll be some bias due to many factors. Okay, reason under etch, over etch, resist lifting, or non-uniform process or non-repeatable process. Hari ni dia etch 10 nano, esok dia etch 9.8, esok dia etch 11, lusa dia etch 8 nano. So it's not repeatable. You want it to be repeatable. Repeatability is another factor. It has to be repeatable. Whatever you do in mass production has to be repeatable. This is another word. You want it to be repeatable. Or another word for this is reproducible. Reproducible. Okay? Mana you run hari ni, esok, lusa, next week, next month, next year sama. Okay, dia punya result sama je. Kalau hari ni lain, esok lain, lusa lain, or it's drifting one way, drifting another way, or fluctuating out of control, that means your process is not stable. Okay? That's what it is. Isotropic versus anisotropic, we discussed briefly before. Isotropic etch is when it etches the etchant, either it's the chemical or the plasma, depending on whether you're running dry or wet process. Etches at the same rate in all directions. Features are enlarged. So assuming you have your molecule kat sini, you be etching kat sini, katalah mula-mula dia tak etch lagi oxide, then it's etching the oxide in all directions. Okay, so dia makan sama je. Then it's going to be isotropic. It's going to be rounded, curvy like this. Okay, so all wet etches and some plasma etches are isotropic. Not necessary, ada juga some cases wet etching yang anisotropic. Okay, for example, TIMA, KOH, with regard to silicon, silicon, I'm talking about etching silicon. So these chemicals towards silicon are all anisotropic. Aniso. Okay. Macam HF on silicon oxide is isotropic. Some plasma etches are isotropic, majority anisotropic. Right, anisotropic on the other hand, you can compare with the previous slide. Okay, resist on oxide. This one resist on oxide as well. Anisotropic, it is highly directional, one direction. As I said, there will always be some horizontal component, but then since the A is very, very high, approaching 1, anisotropy, vertical minus horizontal over vertical, right? So approaching 1, so that means it's highly directional, one direction. Component horizontal is very, very, very small. Feature sizes are preserved and side walls are nearly vertical. So your feature size here referring to the CD size, CD of the resist is preserved and side walls are nearly vertical. Even though you don't get perfectly vertical, but it's nearly vertical. Usually a bit, usually it's a bit plus. Okay. Aspect ratio is another factor that you have to understand. The complexity of the edge is dependent on both the width and the depth. Okay, width, depth. So these are the two dimensions that you have to look at in order to calculate aspect ratio. And AR, aspect ratio, is given by depth over width. Okay, so as the aspect ratio increases, the difficulty of the edge also increases. High aspect ratio means high depth over small width. Okay, for example, kita tengok oxide, oxide on the three diagrams below. So the first one, if you have your AR of the oxide, AR oxide is 1:1, so that means your depth over width is 1:1. Depth 1, width 1, right? So depth, let's have a look at the depth. This is the width, this is the depth. So depth over width is 1:1. Lebih kurangnya saja. Right? On the other hand, you can also have AR of 2/1. Okay, so that means your depth is double your width. Sama width, but then your depth is double. So your aspect ratio is then 2. Ataupun 2:1 lah, atau you can just say aspect ratio equals to 2. That means 2:1. On the other hand, you can also have half, 1/2. Okay, your depth is half, your width is the same, but then your depth is half of the width. Okay, then you get your aspect ratio to be half. So as the aspect ratio increases, for this particular case, 2/1, the difficulty of the etch also increases. So if you want to etch, then it's gonna demand higher quality etching process because dia lagi dalam. So therefore you have to ensure that it is able to etch your oxide uniformly, anisotropically. Okay. So for example, anisotropic etch, deep silicon etch 4/1. Okay, depth over width 4/1. Maybe lebih dari 4 actually, right? So this is silicon. You want to etch silicon anisotropically. You can see here it's not that anisotropic for some reason. Ada lebih-lebih kan. But then the whole idea is etching like that, just like it's digging a well. Okay, anisotropic process. The process A is probably very close to 1, and then if you get a depth over width, I think it's, so that's probably there, yeah, about 4 to 5/1 perhaps. Yeah. Okay, so AR is 4. This is very, very deep. Characteristic of wet etch. So now let's talk about wet etching. Usually it's highly selective, just like what we discussed on HF to SiO2. Isotropic usually, except for those which are anisotropic. Okay, tak semua wet etching isotropic. Okay, some are anisotropic. And when you talk about etching, you have to understand that it's not always silicon that you want to etch. You want to etch silicon oxide, silicon nitride. You want to etch some metals. Okay, so when you talk about selectivity, you're talking about the selectivity of the material to be etched with regards to the chemical that you want to use for the etching. For use on features larger than 3 microns, usually, but it can also be done on nanometers now. Okay, boleh je pakai nanometer sekarang. For example, our black silicon research, it produces nanowires macam ni. Nanowire ni silicon, so asal dari silicon wafer. So kami just etch masuk dalam je. So this width is like 100 nano or so, 100 nano. And the height can be up to micron. Typically, we do 500 nano. Lebih kurang. So what is the aspect ratio for this case? Berapa aspect ratio dah for this particular structure? Our black silicon PSI. Berapa aspect ratio dah? for this particular case? Anyone? What is the AR? Right? 5/1, right? Very good. Okay, so it's 500 over 100, depth over width, 5/1. Okay, nak letak dalam apa pecahan pun boleh macam numerator denominator 5/1 can as well. You can also say AR equals to 5, same. So bila you cakap AR 5 tu maksudnya 5 with respect to 1 lah, dah divide lah. It's understood, right? So high throughput, usually a wet chemical is high throughput if you compare to a dry process which uses plasma. It has to be in vacuum condition. Bila vacuum ni dia lambat sikit lah, because you have to pump down the chamber down to certain vacuum level, and that takes time already. Okay, and on the other hand, if you use wet chemicals, you don't have to use any vacuum condition. Cuma you have to have like what do you call that? Chemical bath. Chemical bath macam sinki besar chemical bath. So you can just use your wafers and dip dalam bath lah. Okay, so one bath can probably fit 100 plus wafers. Okay, mungkin kalau one pot consists of 25 wafers, probably you can fit a couple of pots at one time in one batch. Okay, so it's a batch processing. And throughput because it is batch processing. In comparison to dry, you kena masuk wafer tak banyak lah dalam chamber. It can be batch processing as well. It's just that it's slower if you compare to wet. But then it has these liquid chemicals. You have HF, you have peroxide, nitric acid, HCl, TMAH, sodium hydroxide, potassium hydroxide. So they are all hazardous liquid chemicals, right? So if you look at HF, for example, this is about removing HF from silicon. Okay, so this is called native oxide. Native, so you tinggal wafer dalam tinggal wafer dalam condition tu there will be native oxide grown on the wafer. It's like 3 to 5 nanometer, very thin, and the quality is not something else, right? Okay, this is the reaction. This is the equation involved. Okay, you can use BOE, for example, buffered oxide etching, in order to run the process. Okay, so first one is etch silicon oxide using HF. The second example is etch silicon using nitrate and HF. You can also do etching silicon nitride using hot phosphoric acid. So ni semua ni dangerous chemical. They are all isotropic, right? So on the other hand, you can also have anisotropic wet etching, even though most wet etching is isotropic. You can also have anisotropic. Okay? For example, KOH, NaOH, TMAH with respect to silicon. So these are all anisotropic to silicon. So anisotropic means it will etch. Anisotropic dia tak semestinya you etch one direction. Okay, it is directional in nature. Maksudnya dia ada certain, it has higher etch rate in one particular direction with respect to the others, and that doesn't say that you can only have one direction and not others. So that's why if you look at this, you guna silicon 100 silicon wafer, when you rendam dalam chemical bath, say ni chemical bath, liquid chemicals semua dalam ni, say containing KOH, which is anisotropic at some temperature, typically above 80 degrees C. Okay, you can also add IPA if you want to. Isopropyl alcohol or other additive can also be added. So what it will do is it will etch 100 plane way faster than 111 plane. So in this case, it's etching both, but then 100 is etched much faster than 111. Much faster than 111. So that means you akan dapat satu, as a result of this, you will get pyramid. Akan dapat bentuk macam pyramid. So if these areas are not etched because it is masked, it is closed. So kalau let's say you buka, you tak ada mask ni, tak ada protection layer. So let me see what is on the next page. Okay, so if you don't have anything on this to cover this, then what you'll get is something like this. You'll letak wafer somewhere, there's no mask at all. You repeat those, you have like tadi. So what you'll get is something like that. Pyramid. Okay, pyramid structures. So this is 2D lah, kita tengok dari tepi cross section. If you look at from an angle, so this and all this, it is actually a pyramid. Actually, pyramid. Then you have your adjacent pyramid. Then you have your adjacent pyramid. Dia dekat lah. The pyramid. So it's random. It's randomly formed. That means the size of all the pyramids are not the same. So they are the distribution. I mean, some are bigger than the others. But then they are pyramids because of the anisotropic nature due to this. So etching silicon using QH, just like what we discussed on the previous page. So etch rate of the R of the 100 is way higher. In this case, about 100 times higher than 111. So below you etch, then you're gonna get this. You're gonna get this plane. You're gonna get that plane. Okay. If you get pyramid like that, this is what you get after QH etch. So these planes, this face is 111. This plane, muka pyramid, all the facets ataupun muka pyramid, all 111. Because they are etched slowest. Sebab tu dia appear, sebab dia lambat kena etch. Okay, yang lain-lain semua dah gone. So yang kalau you tengok muka pyramid, you tengok pyramid kat Mesir kan. You tengok je pyramid tu. So that will be exactly the pyramid that we're going to get on silicon if you use anisotropic etchant like TMA, KOH, NOH. And the faces of the pyramid dekat Mesir tu is 111. Okay, it's 111. So that's what it is. So kita akan pakai pyramid ni extensively in solar cell fabrication. Kalau you get to go to silicon solar companies like JA, Jinko, QCell, Hanwha QCell, some other SunPower perhaps. So they're all using these upright pyramids. So upright pyramid macam biasa tu upright. Okay. So you can also design your device to have inverted pyramid. Boleh juga. Maksudnya pyramid tu instead of like that, dia masuk dalam. It's called inverted pyramid. Masih pyramid, but then it goes inwards into the surface. Maknanya tak ada nampak macam tu lah. Semua masuk dalam. Okay, so that's called inverted pyramids. But this particular case is called upright pyramids. Okay. Jadi kalau you pergi solar company, then you will know this. You will learn about this if you are in charge of etching process. Upright pyramids. The size is typically around 5 to 8 micron. Okay, 5 to 8 micron. And the angle here, due to the lattice punya ni, if you angle, if you look at that angle with respect to the base, theoretically it should be 54.7 degree. Okay, theoretically. So maknanya ni face yang 111 tadi lah, kita tengok di tepi sekarang. It should be 54.7 theoretically, but then in the industry, it's since we have a distribution of pyramids, ada satu yang ada yang besar, ada yang kecil, ada yang slightly steeper, ada yang slightly tak steep sangat. So the distribution is usually between 48 to 52 degree. This in real case. Tapi theoretically it should be 54.7. Okay, but due to some uniformity issue, we have 48 to 52 degrees as our distribution. Okay. So wet etch process cycle, what do? Let's go for another few minutes. So what do? We etch using the etchant, either it's isotropic or anisotropic, depending on the process. Then we rinse during after the etching. Sorry, after the etching we rinse. Kita basuh dia using the eye water. Okay, and then we dry. We blow dry the wafers. Sebab wafer tu kena dry. Okay, kalau you ada some droplets, then it's going to be something else. It's going to be defects and stuff, right? So it can be dried by centrifugal spin. Yang spin dalam mesin tu macam konsep mesin basuh kan, spin. Tapi dia spin wafer lah. Okay, it can be vapor dry, jet dryer. It can be compressed nitrogen. Okay. In the manufacturing of large-scale electronic IC, wet etching is being replaced by dry etching. Not entirely true for all cases, but we have quite a lot of dry etching as well. So wet etching is mostly anisotropic, but not necessarily true. We discussed about 111, 100 now, which is anisotropic. Wet etching has poor resolution. So that means if you want to go for a very small feature size, then the control over wet etching process is less. So the control is not as good as the dry process. Okay. So yeah. Unless you can prove that you can have better control over the process by using wet etching. Wet etching depends on a lot of corrosive chemicals which are harmful to human bodies and environments. Yeah, wet etching needs a large number of chemical reagents to wash away the residues, which is non-economical. Sebab dia pakai bath, dia pakai sinki besar, chemical bath. Then you have like one batch of wafers, 25 wafers, another batch 25, another batch 25. Tengok lagi panjang, lagi banyak lah wafer masuk. So it's a batch kind processing. So etching requirement at nanoscale, this is not really small yet. Okay. 150 nanometer height, 50 nanometer width, more or less. You can see polysilicon is there, and nickel silicide, NiSi, nickel silicide is deposited on polysilicon, and you have spacer at the side. This is a spacer. Nanti take aja, don't worry yet. This spacer, Y spacer, let's discuss later on. So obtain desired profile, slope of vertical, minimal undercut, selectivity, uniform and reproducible, minimal damage to the surface, clean, economical, safe, right? So isotropic, we've discussed. Okay, anisotropic, just like that, but this is not really highly anisotropic. It's still, you can still see some undercut here, but it's not as bad as anisotropic on the left. Completely anisotropic is like this. So this one probably A is close to 1. Okay, kat sini mungkin A is like, I don't know, 0.7 perhaps. So quite anisotropic, but not entirely anisotropic. So what's the A for this? What's the A for case number 1? What is anisotropy? Anisotropy for case number 1. What's the value? Bukan aspect ratio, huh? Anisotropic. What's the value for the first one? The second one is 0.7. The third one is 1. And what's the value for the first one? Anyone? 0.3? Yeah, maybe 0.3, 0.2. Unless it's isotropic, okay? Kalau dia completely isotropic, then it's 0. Okay, kalau sikit-sikit ada 0.1, something like that, 0.2. Kalau completely isotropic, then 0 lah, tak ada value. Because it's just isotropic. Right, dry etching, let's cover another 5 minutes, I think. Right, what's dry etch, anisotropic or unidirectional? Okay, we've covered briefly just now. So basic mechanism, there are sputtering process, chemical etching, and then energy-driven ion enhanced etching. Okay, ion enhancing ada dua, so inhibitor, protected, energy-driven. Can also use plasma reactors. This is the equipment. Reactor ni dia punya chamber lah. So barrel etcher, parallel plate, high density plasma. Okay. So anyone did any etching before during FLP? Anyone working on etching this time? Ada? Ada any project buat etching ah? Did you etch anything? Anyone? Remove something ke? Ada ke? Kot lah ada etching oxide, nitride ke, etching metal ke, lift off metal ke, tak ada eh? Right, that's right. That's fine. So dry plasma, okay, plasma we've discussed. Plasma is ionized gas. Okay, typically we use argon, and to be able to generate argon plasma, you need to strip off the valence electrons from the argon. Okay, Ar comes in, and then you strip off the valence electrons. So that means Ar minus electron, then producing Ar plus. Okay, Ar plus. Ar plus will be the argon ion. So if you have a cloud of argon ion, then you're going to generate plasma at some level. Okay. Plasma dry etch process characteristic: less selective anisotropic etch is possible for etching features smaller than 3 micron. Well, typically we use for small features because it has a better control over feature uniformity. Okay, dia lebih senang control berbanding wet etching. Wet etching lebih susah control sebab dia liquid. Bila dia liquid dia macam the dynamic of the process is harder to control. Okay, you can produce something, but then to guarantee a very uniform, reproducible features on the wafer will be a bit difficult, especially if you're working with very small size. If you're talking about microns macam pyramid tadi, yang tu memang tak ada apa lah. We just repeat the very same process parameters, then you will normally get what you want to get, unless ada drift dalam wet chemical. For example, before I continue here, let me just finish off with wet chemical somewhere here. Okay, say if this is a real issue, katalah you supposed to etch say how much, 100 nanometer per minute. This is your etch rate, R etch rate of silicon, for example. Then so that means if you etch your silicon for 3 minutes, you should be removing 300, right? So you run 3 minutes, then you should be etching 300 nanometer. It's about 100 nanometer per minute, right? So 300 over 3 is still 100. But at some point when you etch too much of silicon, ini dia punya bar, dia punya liquid. When you etch too much of silicon, that means you remove too much of silicon from this wafer. So you're gonna have a lot of silicon residue dalam bar. Then at that point, if it's too much, then you're gonna have a lot of silicate. Silicate. So the punya residue there is too much. Then the residue then will alter the etch rate, because the solution is no longer pure. So you started off with KOH, for example, pure KOH of concentration X at some temperature. Dan bila you dah etch terlalu lama ataupun terlalu banyak you etch silicon, then concentration of QH will no longer be exactly X. Dia akan diluted, and there are some other stuff dalam chemical bath, and that will alter the etch rate. Kalau dia dah jadi impure, that means the etch rate should be reduced, and perhaps you are not etching 100 nanometer per minute anymore. So perhaps you are going at 85 nanometer per minute with after a certain time. So that will change the material that you remove from the silicon. So you end up having thicker silicon left on the wafer after the very same time, due to variation of etch rate or drifting of etch rate due to a generation of silicate in the bath. So these are among the things that need to be monitored by etch process engineer. Etch process engineer ni kalau dalam fab is Kalau dekat Sitera lah, I don't know about, I'm not sure about other place, but Sitera, Edge process engineer will be the most busiest engineers. Edge ni banyak isu, and isu dia complicated dan they cannot rework, so that's the problem. Okay, kalau foto dia ada isu, they still can rework, strip off the resist and go back to the CED. But then if you etch, if you got it wrong, then you have to scrap the wafers. So that makes your issues to be besar lah. Okay, bigger issues. Right, guys, that's all for today. Let me just stop here and we'll continue with the dry etching next week dah cuti kan. Allah Akbar. Okay, tomorrow no class. Okay, Friday will be test 1. Okay, kita stop kat sini dulu. Nanti after mid-sem break we'll continue with etching, dry etch. Please keep me reminded. So for this Friday we'll have test 1 during 10 to 12 during class time. Okay, 10 to 12. So saya akan upload the question on eLearn before 10. Okay, and then you have 2 hours to go through the test. It's going to be open book. Okay, it's going to cover from day 1 until lithography. Okay, konsep dia macam ZAT487 dulu. Okay, that's how it goes. And then towards the end, you have to upload your answer in PDF format on eLearn. Okay, before 12, right? So 2 hours, 3 questions, test 1, right? So do you have any questions on test 1? Anything to ask before I finish the class today? Ada soalan apa-apa?
2 jam je lah kan, Doktor?
Yes, kali ni 2 jam.
Berapa soalan?
3 soalan.
Okay.
Ada soalan lain? Tapi soalan tak susah pun, don't worry. Soalan dia will just be around what we discuss in the class. Here and there. Okay. It's an open book anyway, right? So you can search online and stuff like that. Any questions on test 1? Ada? All good? Okay, so right. So you study accordingly. Nanti tak ada kelas hari Jumaat lah. Just test 1 for 2 hours and then your next week will be mid-sem break. So we'll see each other after mid-sem break. Dah bulan 1 lah kan lepas tu kan? Hold on, let me see the calendar. 17 ni bulan 14. Then mid-sem break. Oh, not yet. So next week will be 20th to 24th. So we'll see each other again 27, inshallah. Okay? 27 Monday as usual. Okay then, kalau tak ada apa-apa itu saja. Bye-bye, take care. Assalamualaikum.